And let me share my screen. Ah, that's the password. Okay, can you see my screen?
Yes.
Okay, great, welcome back. So this is the last part of the reinforcement learning tutorial. My name is Akshay, and today, so we're gonna talk about some more foundations of reinforcement learning. I hope you had fun with the recitation. I did see some people working on it, so that's great. Of course, we'll leave those problem sets up so you can work on them later on your free time or whatever. Okay, so in the first part of the tutorial, Wen talked about some of the basics of Markov decision processes, and he talked about these three challenges: credit assignment, exploration, and generalization. Just as a recap, so credit assignment is this issue of when you make a sequence of decisions and you observe some outcome. Maybe you're playing chess and you played the whole game and you observe that you lost. How do you know which actions caused you to lose, right? So you made many decisions and you don't know which ones are good and which ones are bad. And credit assignment is this challenge of sort of figuring out which ones are good and bad. Exploration is this challenge of, you have to observe all these things in the world before you can know how to behave, right? So you have to make decisions deliberately to find new information. And generalization is the thing that probably most of you are familiar with if you come from like a supervised learning background, where you see some pictures of cats and you want to be able to predict that other pictures are also cats, right? But you will never see those pictures in your training set. And what Wen talked about were two algorithms that address two of these issues separate together, but don't address all three. So these policy gradient methods deal with credit assignment, and they can deal with generalization, although we didn't talk about it too much. And this UCB-VI method deals with credit assignment and exploration. But since it maintains this tabular representation and fits the dynamics in this sort of, it learns about each state individually, it's actually not able to generalize across the states or actions. And in the last maybe 5 or 6 years, there's actually been a lot of work in the reinforcement learning community trying to get algorithms and understand what is possible when all three of these challenges are all in the picture. So that's what I'm going to talk about today. And it's going to be a little bit more high level than what Wen presented. So I'm going to try to just tell you some of the key conceptual ideas and some of these constructions for how algorithms might work, but I'm not going to go into any serious details about the proofs and stuff like that. And because of that, if there are questions, please stop to ask. I think we should have plenty of time. And there's a third part, but if you don't get to it, it doesn't really matter that much. So we should have plenty of time. Okay, so just to sort of formalize some of this stuff, let's focus on the episodic setting. So this is not the discounted one that Wen talked about most of the time, but the one that he analyzed UCB-VI in. So there's going to be a finite horizon, and the horizon is going to be capital H. And when we talk about generalization, I want to stay relatively abstract. So I'm going to give you some function class, script f, and it will have some type that I'll explain later. And what you want to do is you want to find a near optimal policy, say like an epsilon suboptimal policy compared to the optimal one, with a number of samples that scales polynomially with some measure of complexity of the function class f, the number of actions, the time horizon, and the approximation or the accuracy parameter epsilon, 1 over epsilon here. And for this complexity, I'm being very vague, but you can think about it like the VC dimension of the function class or the log covering number or something like this. I think for most of the results I show you, I'm going to assume the function class is finite, and I want complexity of f to be like log cardinality of the function class. Okay, so this is sort of like at a high level what we're going to try to do. And this is, if I get something that looks like a statistical learning generalization bound here, then this is going to be why I say this is like capturing this generalization challenge. Okay, so let me explain some possible types for this function class script f. So the first one, which we typically call policy search, is that your function class is a class of policy. So these are mappings from states denoted by X here to actions or distributions over actions. And this is sort of like the most direct thing. And this is like what you might try if you're trying to do a policy gradient approach. You have a class of policies, they might be parameterized in some way, and they just directly map states to actions. And here, we'll see that some assumptions on these problems are quite necessary. And so the most natural sort of realizability assumption is that you actually have the optimal policy in your policy class. So this will be like policy-based realizability, right? So this is one type for your function class. Another type is referred to as value-based methods. And here your function class maps states and actions to the reals. And this is like a class of candidate Q functions. So these are functions that are supposed to score state action pairs in terms of their long-term cost or long-term reward. And again, you might want to make some realizability type assumption. And the natural one to make is that the Q star function, this optimal value function, is in your class. And this is like maybe a nicer setting to think about because you have this Bellman equation. So remember that this is how we define the Q star function. So the Q star function, it takes a state and an action, and it outputs the expected future reward, given that we start in the state X and the first action we take is A, and we behave optimally from then on. So this is like the definition, and this Q star function satisfies this Bellman equation that we saw before. And so when you think about value-based methods, it's quite common to use something like this Bellman equation as your learning signal for trying to learn the right Q function. And the last approach, which we'll touch on maybe at the very end, are model-based approaches. So here, the type of your function class, they map states and actions to the reals and distributions over the next state. And here I'm actually just trying to directly fit the dynamics of the entire MDP. And again, you can say there's a realizability assumption where the true dynamics are in your class script M. So these are the sort of different types. I think one theme I'm trying to convey is that there's a lot of different ways you can attack reinforcement learning problems. And you can try policy-based, value-based, model-based, all these things. There's many, many variations on all these problems. And as far as I know, they're all quite interesting. So, you should try various things with all these definitions. Okay, so today we're mostly going to talk about value-based methods. Okay, so I guess the first main concept that I think it's important to cover is this notion of distribution shift. And this is a key challenge in all of these reinforcement learning problems. And this is kind of what makes reinforcement learning different from supervised learning. So here's a classical and very general lower bound. So suppose I give you a finite class of Q functions, script F, and I promise you that the optimal Q function, Q star, is in this class script F. So this seems like quite a nice situation for you. Yet, what you can show is that you still need either A to the H over epsilon squared samples or cardinality of F over epsilon squared samples. And I guess what I want to say is that both of these bounds are not good enough for our goal. So somehow A to the H is scaling exponentially with the horizon, which means we cannot solve any problem of even moderate horizon. And cardinality of F over epsilon squared is somehow not capturing the fact that I should be able to generalize, right? This is sort of like exponentially worse than what I could get if I were in a supervised learning setting where I should be able to scale just with the log cardinality of the function class. And what's highlighted here is this notion called distribution shift, which is just that even though I can predict Q star accurately on some data that I've already collected, it actually does not imply basically anything about whether I have a good policy in my hands or not. So basically the data that you might train your function is not going to be the same as the data where you evaluate your function, because your policy that you get might go somewhere else. And so here's like a kind of example and basically how this construction works. So consider a tree where the circles are the states and the arrows are the actions. And it's a tree with exponentially many leaves. So there's 2 actions and the depth is H. So there's 2 to the H leaves. And one leaf has a reward and all the other leaves have no reward. So suppose I give you a data set that is supported like on the right half of the tree. Okay, and the data set is supported over here. So you can find a function in your function class that approximates the Q star function on this data set. You can get it basically exactly. The issue is your function, there's no way you can get your function to be correct on the left half of the tree. You just don't have any information over there. And so the thing is, okay, a good policy, or even a policy that's following your function, will go to the left half of the tree because that's where it thinks there's reward. But once it goes over here, you sort of lose track of what it's going to do because you don't have enough information to decide that it should go to this leaf instead of this leaf. And so this is sort of the problem with the distribution shift. You might find a good Q function. It might be very accurate on the data that you have, but the induced policy will wander off of the data set that you have. And once it wanders off, you don't know what's going to happen. Okay, so this is sort of like the main problem, I think. This is one of the main problems. And basically, as far as I can tell, there's like two kind of conceptual approaches to dealing with this. And the first one is kind of you assume that the function class has some structure that addresses distribution shift directly. And I think most people, or I don't know, I like to call this the function class can extrapolate. And we'll see some examples of this in the coming slides. And the other one is actually like you're making some assumptions about the way the environment is structured. And here, what I like to think about this is like the environment somehow only has a few distributions. And so if you collect data from all of them, then you actually can generalize. And we'll see examples of both of these as we go. Okay, and basically, you know, if you start paying attention to the RL theory literature, you'll find that there's this like zoo of reinforcement learning models where people are thinking about them and trying to show that, you know, these problems are learnable and so on. I think basically all of them can be pigeonholed into one of those two conceptual approaches. But it is kind of, you know, if you're a newcomer to the field, I think it's quite complicated. What I'm going to try to do is explain to you some of these like unifying themes. So one thing that like happened quite recently is this, it was sort of observed that a lot of these problems have some sort of like low rank structure. And for all of these problems that have a low rank structure, you can like show that they're learnable using some very, very nice general framework. And this is the bilinear class. And I'll tell you about that towards the end. But here are sort of a lot of the buzzwords, and we have all the references in the tutorial page. So if you want to learn about these things in more detail, please just take a look or come talk to us about it. But yeah, I think hopefully at the end, you might not know what all these things mean, but actually you'll probably know how to analyze them as soon as you read what the definitions are. Okay, so now's a good time to stop if there are any questions. When?
So I've been answering some questions there, but maybe there's one question from Robin. So he's asking, can we restrict the policy not to go to those, regions that are not covered by the training data?
Yeah, so that's a great question. And in some cases you can, but in this problem, if you restrict the policy to not go to the places covered by the, if you restrict the policy to stay in the support of your data distribution, somehow you can't produce the optimal policy in this case. So if you want like a global optimality guarantee, you really do need to worry about the case when your policy wanders off, because that's where it might be getting reward. But there are definitely works that are finding mechanisms to restrict the policy to stay on the data set. And there are problems in which that is actually the right thing to do. Okay, cool. So if you just glance at this thing, you'll see the word linear appears a lot here. Linear is over here and over here. So let's start out with linear methods. Okay, so linear methods are the ones that use linear functions to approximate the Q star or various quantities. And linear functions, as we'll see, support extrapolation. So this will be sort of like the conceptual approach 1 to dealing with distribution shift. Now, the most basic question when you think about linear function approximation is the following one. So suppose I give you a feature map that maps states and actions to d dimensions. That's called phi. And I promise you that the Q star function is a linear function in your features. Okay, so this is the promise. This is linear function approximation with linear realizability. Now, if I promise you this, is it possible to achieve polynomial in d, h, and 1/epsilon sample complexity? Okay, so this I think is the most basic question. If you have thought about supervised learning problems for supervised learning, the answer is yes. If you've thought about bandit problems for bandit learning, the answer is also yes. So, and the strategy to do this is you basically, for bandits, you'll query on a basis. So maybe you have all these feature vectors and you'll query on the 2 blue ones. And once you know the reward on the 2 blue ones, you'll be able to infer the reward on the orange one because it's in the span of the other two. Right, so this is a very natural strategy. You can query on some points that span your space of features, and once you know the answer on your spanner, then you can interpret or extrapolate the answer anywhere else. So because this is sort of, I don't know, kind of easy in supervised learning and bandits, it's very natural to ask what happens when you have a longer horizon. So what about for reinforced learning? Is this possible or not? So this brings me to this kind of recent and very cool body of work on linear function approximation that I like to think of as an arms race. And it turns out that the answer to that question is no. But this is a very, very recent result that culminated in a long body of work on upper bounds, which I'm highlighting in green, and lower bounds, which I'm highlighting in red, for various linear function approximation settings with various assumptions and various different types of algorithms. And so here I'm just saying, here are the assumptions. Again, I don't expect you to understand everything here. Here are the setting, and red is lower bound, green is upper bound. I guess what I'm trying to show you is that this is actually a very delicate situation, because there are some rows that look almost the same, and they're exponentially different in terms of their complexity. So if you look at this one, this is this linear Q star plus gap, and this one is also linear Q star plus gap. The only difference is whether you're in some planning setting or in some exploration setting, and the difference is polynomial sample complexity versus exponential sample complexity. And the same thing is going on here in this linear Q pi for all pi. There's some exponential separation between two different reinforcement learning settings. So while the linear case is somehow kind of easy to understand for supervised learning and bandits, it's actually quite subtle for long horizon reinforcement learning. And so this is actually highlighting some other challenge. So we have this challenge of distribution shift, and this is sort of addressed by the fact that linear functions can extrapolate. But there's this other challenge that arises when you think about long horizon problems, which is that there's some notion of error amplification when you do dynamic programming. So when all you know is that Q star is linear in your features, somehow the most natural thing to do is these dynamic programming type approaches like value iteration that Wen talked about in the first part. But because you're using function approximation, when you try to apply this Bellman operator to some function that maybe is not Q star, then you might get a function back that's actually not linear in your features. And so you have some additional error that's incurred by applying this Bellman operator to your functions. And this error amplification turns out to be quite a headache. And it's sort of the source of a lot of these hardness results. So let me just tell you about one of them because it applies to the online exploration setting that we're kind of focusing on. I'll just tell you about this very, very informally. Okay, so this is this result by Rusang Wang, Yuanhao Wang, and Sham Kakade. And what they show is that there exists some class of linearly realizable MDPs. These are ones for which Q star is a linear function in the features. There are some gaps, which doesn't really matter right now, such that any online algorithm requires either 2 to the D or 2 to the H samples to obtain a near optimal policy. And so this is based on some construction that it's like a variant of this one by Weiss, Amartilla, and Shepesvari from the planning setting. And I think that the first idea is to use Johnson-Lindenstrauss to find exponentially many feature vectors that are near orthogonal. And okay, so once you have, okay, if this were truly orthogonal, then somehow your problem is just done because you could set the reward function to be 1 on one of these and 0 on all the other ones. And now the agent has no choice but to sort of try all the feature vectors, right? Of course, you can't do that because they're not truly orthogonal, they're just near orthogonal. And so there is going to be some information leakage, right? And so what these constructions do is they, in some very clever way, they show that when you play the wrong action, you only recover some exponentially small amount of information. And to do this, you have to do some quite intricate construction that I don't really want to go into, but I think this is sort of the high level idea. There's one action that's the right answer. And if you play it, you know everything about the problem. There's all these other actions whose features are near orthogonal. And using the multi-step nature of the problem, you can make it so that when you play the wrong action, you recover an exponentially small amount of information. And so now you have to do this exponentially many times in order to find the right action, or you have to guess correctly. So this is sort of how these constructions work. And this is truly quite different from supervised learning and bandits. So in bandits, you can try the same strategy where you have exponentially many different feature vectors and they're all near orthogonal. But now somehow when you play the wrong one, you'll recover a polynomial amount of information about the underlying parameter. And you somehow can't make it so that you can only recover an exponentially small amount of information. So this is truly, the multi-step nature of this problem really does make it quite different from supervised learning and bandits. And this is due to this error amplification thing going on. And I guess the point I think that is sort of important to make here is that reinforcement learning really does require strong assumptions. And I think this is kind of annoying because we're theoreticians and we like elegant and beautiful problems. And these problems just require more assumptions. And so they're a little bit more messy. I think, technically they're still quite beautiful and they're really fun to work on. So I don't want to discourage you, but the problem statements do actually require these assumptions in order to get interesting things to happen. Okay, so that's a lower bound. So we can also ask, so now that we know that linear Q star is not enough to enable efficient algorithms, you can start asking what are the assumptions that do enable efficient reinforcement learning with linear function approximation. So let's discuss one upper bound. So this is a setting called a low rank or linear MDP. And here we're going to make actually an assumption about the dynamics and the reward structure. So the assumption is I have my transition operator P, and I'm going to write it as a matrix where the rows are indexed by state action and the columns are indexed by the next state. And the linear MDP assumption is just that this matrix admits a low rank factorization where, in terms of my features phi of xa and some other thing mu of x prime that I don't actually need, right? But this dynamics model admits a low rank factorization in my features. Or to say it another way, the transitions and the rewards are actually linear in the feature map. Okay, and this actually addresses this error amplification issue due to the following lemma. So for any function g that maps states and actions to the reals, there exists some d-dimensional vector theta such that the Bellman backup of function g is a linear function in my features with coefficients theta. And just remember the Bellman operator is displayed here. So you see now when I take some perhaps wrong guess for Q star and I back it up in using the Bellman operator, when I'm doing dynamic programming, I will indeed get a linear function, which is great because now sort of the regression problems I might create will always be well specified. Okay, so this is the problem, and I mean this is the setting, and you can write actually what I think is quite a clean algorithm. It's called LSVI UCB. LSVI is least squares value iteration. UCB is upper confidence bound. And so here's how it works. So you have some data, and you're going to do this in the beginning of an episode, you're going to do dynamic programming with some optimism. Okay, and so what you're going to do is you're going to start from the last time step, capital H. You're going to get a Q hat function, Q hat capital H, and you're going to do linear regression to fit a coefficient vector onto this is the Bellman operator, right? So this is the reward plus the Q function at the next time. And you're going to do this linear regression and you're going to get some coefficient vector theta hat H. And then you're going to define the Q hat H function, the one for the previous time, by applying your new coefficient vector to make a prediction and adding some bonus to account for the uncertainty in your least squares problem. And when you think about these linear regression things, or if you are familiar with linear bandits, somehow the most natural bonus is this elliptical one. So here you're going to look at the norm of the feature vector in the second moment matrix defined by the features used in your regression problem. And this is sort of the right notion of uncertainty. And in the tabular case, this is exactly related to this counts that you saw in the recitation. Okay, so now you define this Q hat function, and then you collect data with the greedy policy that is induced by this Q hat function. So that's the algorithm. You just keep doing this. You do dynamic programming, you do this optimistic definition of Q hat, and then you apply the greedy policy. So this algorithm has a very nice theorem that was proved by Jin, Yang, Huang, and Jordan. So in the low rank or the linear MDP, this algorithm has a regret that scales like square root d cubed h cubed n over n episodes with high probability. Very, very clean theorem, very clean algorithm. It's great. So let me just tell you a little bit about the analysis, because if you did work on the UCBVI thing, it is actually quite similar. So just like you may have seen in the recitation, if your bonus is valid, so it actually dominates the prediction error of your regression problem, then you can show this sort of regret decomposition, where the regret is upper bounded by like the sum of the bonuses on the states and actions that your agent is collecting. Okay, so this is, you're just going to use this, like you're going to use optimism and you're going to use this telescoping decomposition that you saw in the exercises. And now, so now you, okay, in order to apply this regret decomposition, you need a bound on the prediction error. And the linear MDP property actually gives you this, because when you do the Bellman backup of some of your Q hat function, this will actually be a linear function in your features. And so you have a well-specified least squares problem where you can actually obtain a prediction error guarantee. So this is quite important for this, preventing this error amplification property and actually getting prediction error guarantees. And the last step is how to control the sum of the bonuses. And for this, we use this elliptical potential lemma, which is, I guess, somewhat classical from online learning. And it goes as follows. So suppose you have these feature vectors x1 to xt that are in the Euclidean ball. And I'm going to define some sort of second moment matrix in this incremental way. So I start out with like lambda times the identity. And then I'm going to keep adding in features, the second moments of my features into my second moment matrix. And now I'm going to look at the sum of the xt's in the sigma t minus 1 inverse norm. So this is sort of the way, the bonus was actually defined something quite similar to this. And so you can show that this sum is always bounded by like square root t times d. And this is actually quite a nice geometric argument that you can find in like many reinforcement learning papers. And if you want to learn more about that, like I can send you some links. And this is sort of the key way. I guess this is the way that I think about formalizing this notion of distribution shift. So if you've seen feature vectors that sort of span the space, then your second moment matrix will be like quite large. And so the norm of some new feature will be small. And that's the way you measure like extrapolation. Okay, we'll skip that. Okay, so let me just wrap up with the linear stuff and then we'll move on to the nonlinear stuff. So when you do linear function approximation, you have some way to handle extrapolation, and this is this elliptical potential lemma. There are some other potential arguments. So there's this notion called the eluder dimension that Dan Russo and Ben Van Roy developed in 2013. It's been studied as well. There's you can also get some results with the eluder dimension. In the linear case, actually, the challenge is not distribution shift, but this error amplification in dynamic programming. And this is avoided in linear MDPs and in this other setting called linear Bellman completeness that I'll talk about in the next part. But I think the main takeaway is that somehow reinforcement learning is quite different from supervised learning, and much stronger assumptions turn out to be necessary. Okay, so there are some open problems here. I think they're on the slides. If you want to think about these problems, come talk to me. I'll tell you more about them. I think they're all still open. Are there any questions?
Yeah, so why the elliptical lemma is important here?
Good, that's a great question. So the elliptical lemma is a way to guarantee that the bonuses do not continue to stay large, right? So I've upper bounded the regret by the bonuses. How do I show that the bonuses somehow go to 0, right? Or the sum of the bonuses has to be sublinear in T in order to get an interesting guarantee. And the elliptical potential lemma is guaranteeing this basically. It's sort of like saying like, if you actually see features in new directions all the time, somehow you can't see new directions forever because there's only D directions in your space. And the elliptical potential lemma is quantifying this. We'll see a slightly different argument that turns out to be quite similar, and you'll see it there as well. Cool. Any other questions? Okay, so let's move to the second part, the 3B part, which is about somehow more information theoretic results that mostly talk about the other approach to handling distribution shift, which is this, I don't know, not too many distributions approach. Okay, so let's start by revisiting the linear MDP. So I've just written, I don't know, the low rank structure up here. So that key lemma I told you before, you can write basically exactly the same thing in the following way. So suppose we have some function L that maps states to the reals. Now, for any such function, there exists a d-dimensional parameter theta sub L such that for any policy pi, if I look at the expectation of L when I'm collecting the trajectory by pi, I can write this in terms of the coefficient theta L and some d-dimensional feature vector that depends on the policy pi. Okay, so this is like almost exactly the same as that lemma I showed you before. And I'm using the letter L here for a reason. But basically, the way I think about this is that somehow every expectation, as you vary the policy pi, so the expectation admits some sort of d-dimensional parameterization in terms of this coefficient vector L. And you can evaluate the expectation of L for every policy pi if only you knew the policy's feature. And somehow the features are only in d dimensions, so there's only like order d distributions in this problem somehow. And the reason I use the letter L is because this sort of suggests a nice like program where you take L to be some loss function that you want to be 0 everywhere. And what you want to do now is you want to find some policies pi whose feature, this thing, you want to find like d policies pi whose features like span the space. And then you minimize the loss on those policies distributions. And if you find an L who's 0 on those distributions and those distributions actually span the space, then your loss is 0 actually everywhere. And so this is sort of the program. So in the next couple slides, I'm basically going to like instantiate this program. Okay, so it's natural to define a loss function. The loss function will have the following type. So it'll take one of your functions in your hypothesis class, and it will take like a tuple of observation, like state, action, next state, reward, and it will output a score. And now what I'm going to do is I'm going to examine this sort of expected loss where there's two arguments. There's f and g here. So the tuple is sort of generated by pi f, okay? But the loss, I'm going to evaluate the loss of hypothesis g kind of on data collected by pi f. Okay, so you should think of this f as the pi here, and this L is evaluating the loss for function g. Okay, so that's the way to think about that. And when you write these expected losses, it's somehow, I like to write them in terms of these matrices. So there's a role in policy pi f and an evaluation function, or a function we're trying to evaluate g. And I'm going to index the rows by the role in policy, and I'm going to index the columns by the evaluation function. And I'm just going to put this expected loss in this matrix. This is only for the analysis. So the linear MDP, it just says for any loss of this type, the rank is less than d, because I can always do this decomposition. Okay, so this is fine and dandy, but what loss function should we take? So that's the question. And while we didn't think about this in terms of loss minimization at the time, it turns out a very natural loss function to take is this Bellman error. Okay, so this is how we're going to derive this quantity called the Bellman rank. So you're going to choose the loss to be the prediction of function g at the current state action minus the reward minus the prediction of the function g at the next state. Okay, and the reason you take the loss this way is because the Bellman optimality equation implies that the loss for q star on any data distribution induced by any function f is 0. So now you have a loss function that you actually want to be 0 everywhere, because if it's 0 everywhere, you have q star in your hand. Okay, so basically if I minimize this loss function over a spanner for the feature induced by these policies, then I have to have q star. And indeed, this is true. And so what you can prove is that if you have a function class that contains q star, and these matrices where you use this loss function have rank at most m, then you can find a epsilon suboptimal policy in a sample complexity that scales polynomially with everything, and only the complexity of the function class, like the log cardinality, say. Okay, so let me tell you a little bit about how you prove this theorem. I mean, sort of the intuition is I've already told it to you, but let me tell you a little bit more detail. So the algorithm we're going to use is this version space kind of algorithm. So you're going to be throwing away functions that have high loss on some distribution that you've seen before. So you have some remaining surviving functions, and I'm just going to keep using script f for that. And you're going to select a function f hat that maximizes this quantity. Okay, so this quantity is the prediction that f hat makes about its own policy at the starting state. So this is somehow like an optimistic guess for the optimal value v star. Because if I put q star here and pi star here, that would actually be exactly v star. Okay, so I'm going to use some sort of optimism to pick this f hat. Then I'm going to collect data with the policy induced by f hat, and I'm going to observe f hat's actual value, or pi f hat's actual value. So if pi f hat's actual value is about the same as this guess, then I guess I claim I have a good policy because I made an optimistic guess. I achieved my optimistic guess with my real experience, and so I must have a good policy. And if it's not, I'm going to do loss minimization. So I'm going to use the data collected by hat f to eliminate other candidates G that have high loss on that data, on those data distributions. So this is the loss minimization. Okay. So that's the algorithm with, I guess, no details, but you can sort of imagine filling everything in. So probably you have to estimate this from sample. So you put like a hat here, and you collect some data from the start. You have to estimate the expected loss from sample. So you put a hat here, and you collect some data using f hat. The point is, like, all the data collection can actually be done just using f hat, and you don't have to explore the whole space somehow. You don't have to try all policies. Okay, so let me tell you a little bit like the intuition about how this analysis goes. So the first claim is that Q star is never eliminated. And I guess you can probably believe this because Q star has 0 expected loss, no matter how we collect the data. Right, so this is just the Bellman equation. This is why we chose the loss function that way. And claim 1 immediately implies that when we terminate, the policy we output is very good. Because so Q star is in our function class, and we are choosing a function that makes an optimistic prediction about the initial value. So in particular, the value that f hat makes is the prediction that f hat makes is always bigger than v star. And so if f hat is actually achieving its predicted value, then it must actually be getting near to v star in terms of the policy performance. Okay, and then the second claim is that you have this telescoping performance decomposition. So if you were doing the recitation, you might have seen these sort of telescoping arguments like in the proof of the simulation lemma. So it's something very similar. But what you can show is that the prediction that a function makes about its own policy minus the actual value that that policy gets is equal to the sum of the Bellman errors for that function. Okay, the loss, I'm measuring the loss of the function f on the data collected by f. Okay, and this is some kind of straightforward telescoping argument. And now somehow using this fact, we are going to show that the number of iterations is very small. And I'm just going to do a proof by picture, and it's going to actually be some linearly independent, independence argument. So let's write this matrix where I have all the expected losses. So the rows are indexed by roll-in policies, and the columns are indexed by the second argument, the function I'm evaluating. So Q star is some function I'm going to evaluate, and claim 1 is just that Q star is all 0 in this whole column, right? So black is 0. Now we have some function f hat, and all of the action will be in f hat's row and f hat's row and f hat's column. Okay, so f hat has survived up until now. And maybe in the first iteration, we collected data from pi hat 1, and that's one row in this matrix. And then the second iteration, we collected data from pi hat 2, and that's some other row in this matrix. And the fact that f hat survived means that these two entries have to be 0, right? Because if these two entries are not 0, that means that F hat actually had high error on one of these data distributions, and then we would have eliminated it. Okay, and then the telescoping performance decomposition is just that this entry is actually not 0. Because if this quantity is big, okay, so if this quantity is small, then we terminate. And if we don't terminate, then this quantity is actually big. And if this quantity is big, then one of these has to also be big. And so let's just imagine we're looking at the H for which that one is big. This quantity has to be not 0. And now you can see that because these two are 0 and this one is not 0, the row, this orange row has to be linearly independent from the previous rows we collected data on. And this is how you show that, every time you do something, you have to find a new direction in this low rank space, I guess. And so you can only find m such directions because the rank is m. Okay, so that's like kind of the intuition for the proof. You have to actually make this more robust. This is sort of where like these elliptical potential type arguments come in. And I won't go into that here. Okay, so I think I just have 2 more slides on this part, and then if the time is too late, we can just stop. Okay, so that's like one instantiation of this program of loss minimization. And it turns out that like you can do this much more generally. And actually sort of what happened is, that paper I told you about came out in like 2017. And then since then, there's been many developments and many new models that have been proposed and studied. And it sort of turns out that almost all of the models that have been proposed and studied can kind of be fit into this program of loss minimization, but you have to change many of the ingredients. So this bilinear classes framework is sort of telling you all the ingredients that you have some flexibility on. And I just want to tell you sort of like roughly what these are. So there's a couple ingredients. There's a function class. And previously, we've always been thinking about a class of Q functions, but this can be something more abstract. Like maybe it's a class of models or something like that. And then you have a loss class where there's one loss function for each function in your hypothesis class. So we'll see that maybe you need to adapt the loss to the roll-in function. So this F is supposed to indicate the roll-in function. And then there's some policies that you're going to use to do the loss minimization. You're going to take actions according to these other policies to do loss minimization. And so for Bellman rank is a special case where the hypothesis class is a set of Q functions. The losses are not really dependent on the function class F, and they're just the Bellman errors. And the estimation policy is just uniform. So this is just like, this is some generalization of the Bellman rank. Okay, and then you have these embeddings that you don't know that map hypotheses into like a Hilbert space or D dimensions. And there's basically 3 properties you need to establish. So, you have some problem, you come up with a function class, a loss class, and these policies, and then you need to show that there exists embedding functions with 3 properties, and then you're just done. Okay. So the first one is that you need to have realizability. So you need that your hypothesis class somehow induces the optimal Q function. Remember, your hypothesis class may be models, but models, you can derive Q functions from them and stuff like this. Then you need this property called Bellman domination. So a hypothesis will induce like each function F can induce a Q function and a value function. And you need that on the data collected by pi F, the Bellman error between the Q function induced by F and the value function induced by F is upper bounded by some inner product amongst your embedding functions. And this is basically this telescoping performance decomposition that we saw in the previous slide. This is just a little bit more abstract way of writing exactly the same thing. And the last one is you need some loss decomposition. So here I'm going to collect data with pi F, and I might use the estimation policy here. And I'm going to evaluate, I'm going to minimize the loss of G. I'm going to look at the loss of G on this data set. And I want this to have some bilinear structure in my embedding space, where I'm going to look at some, one of the embeddings is of G and one of the embeddings is of F. And if you just have these 3 things, so this is kind of like the fact that this matrix I wrote before is low rank. When I minimize the loss, I get this low rank structure, this bilinear structure. And so any problem for which you can write these things down, you can scale with like the dimensionality of the Hilbert space or like the effective dimensionality of the Hilbert space. And it turns out that this framework actually captures many, many things. So, the picture I showed you at the beginning with all these names, these buzzwords, I'm showing them all again to you here. And all of these models can be, you can instantiate the ingredients of the bilinear class framework to show that they are statistically tractable. And actually, all of the things that they changed do matter. So here you kind of want to use a different estimation policy. In this problem, you kind of want to use a different loss function for each F. And in this problem, you actually want to use dynamics models for your hypothesis class. Okay, so let me tell you about this one more setting because I think it's kind of interesting. So this is the linear Bellman complete setting. So here's some assumption. So we have d-dimensional features. So for any d-dimensional vector theta, let's suppose that there exists a different coefficient vector w, such that the Bellman backup of theta, which I'm writing it like this, is actually a linear function in the current feature, okay, with the coefficients w. So this is some assumption that prevents error amplification, because now when I try to do a Bellman backup of a linear function, I will also get a linear function, right? So the regression problems that I might write down in dynamic programming will be well specified. So this is actually quite a standard assumption in the analysis of dynamic programming algorithms, but it's actually unclear if this LSVI UCB algorithm works, because in LSVI UCB, we actually don't back up linear functions. We back up these linear functions plus a bonus, and the bonus is not a linear function in the feature. So in LSVI UCB, you actually do have some misspecification, and so it's unclear if that analysis will go through. But this setting actually does have low Bellman rank or fits into the bilinear class framework via the following kind of elementary calculation. So if I look at the Bellman error for some policy pi f of some parameter theta g, this is just the definition, right? This is the prediction at the current time, and this is the prediction at the next time, and this is the residual. And using this assumption, I can write r plus this max as a linear function of the current feature. So I can write the second two terms as wg times phi. And so now I can push this expectation over here, and you can see that the first two terms depend only on the function I'm evaluating g, and the second two terms depend only on the policy I'm using to collect the data, pi f. And so you see that this problem has some low rank property, some d-dimensional structure. And so immediately you can see that this setting is statistically tractable. This paper actually does this in some other way before the bilinear class thing came about, and they also show that it's statistically tractable. And here, if you actually use you instantiate the estimation policy in some other way, you can actually avoid some dependence on the number of actions. Okay, I guess the last point to make on this is actually this assumption is still crazy strong, because this assumption is somehow not closed under adding features. So if you have a d-dimensional feature map and you add one extra feature, perhaps a linear function that uses that extra feature will not be able to be written as a linear function the previous time, right? So somehow, if you think about realizability, adding features is fine because you can just set the coefficients to 0. But if you think about these sort of completeness assumptions, adding features is not fine at all, because you have to start thinking about what happens when I try to make predictions on functions in terms of those features that I added that perhaps don't actually matter. So this is still a very, very strong assumption. Okay, now is a good time to stop for questions, and perhaps stop entirely. When are there any questions?
No.
Okay. Are people lost? Okay, maybe. Okay, let me look at the chat. Do people want to go on for 10 more minutes, or do people want to stop now? Maybe just type yes or no. Could I explain the two embedding? Okay, people are saying yes, let's continue. Great. Okay, we'll go on for 10 more minutes. Let me answer Furong's question. Could I explain the two embeddings on slide 19? Yeah, so Furong, if you look at okay, when I say that this Bellman, this ecal matrix is low rank, it means that there's an embedding for the roll-in policy and an embedding for the evaluation function, such that every entry is given by their inner product, the inner product of the two embeddings. So the embedding on slide 19 is just the same thing. It's saying, when I look at this loss decomposition, I'm going to write an embedding for the roll-in policy and an embedding WHG for the function I'm trying to evaluate. And so this is just saying that if I looked at this matrix with this entry where the rows are indexed by F and the columns are indexed by G, it's just saying that that matrix is low rank. Okay, cool. So let's go on to the last part. Okay, so part 3, oh, this should be part 3C. Okay, part 3B was about kind of like information theory, because those algorithms that I'm showing you are kind of, they're version space algorithms, and they kind of operate by enumerating the functions that you have. And this is kind of problematic because the environment assumptions that we're making actually do permit the state space to be very, very large, but you want to start using like, regression and maybe neural networks to approximate the Q star function and all these things. But if you're enumerating, then you really just can't do that computationally. So then the last part is about how to design algorithms that are, actually practically implementable. So let's start with one special model, which I kind of like. So this is going to be a rich observation problem with a discrete latent state, and the agent is not going to see the latent state. So here's sort of how it looks. There's some latent state, that's the blue cloud. The agent never knows what it is. The agent instead sees an observation. And the picture I like to think about here is like we're in some navigation task. And the latent state is the actual position of the agent. And the observation is like some image that the agent gets. Okay, so the agent looks at the image, takes an action, transits to a new latent state, sees a new image, and so it goes. And you see, this is the kind of problem where, like, because I'm operating on image space, I really want to use like convolutional neural networks to generalize across images, because the space of images is enormous and they're highly structured, and I need to use like a nice, big function class. But if I'm using convolutional neural networks, I really don't want to do enumeration. Okay, one assumption that we'll make is that the latent state is actually decodable from the observation. So that means that like there exists some function that maps the image to this like XY position of the agent. And partly this is because I don't want any partial observability. I want like the process should actually be Markovian on the images. Okay, so this is some problem that is actually the problem we started working on when we started thinking about how to do nonlinear function approximation at all. And statistically, this problem is like kind of boring because the Bellman rank is just the number of latent states. And so we know that this problem is tractable. This is actually like a kind of easy calculation, and maybe you can try to do it as an exercise. So that's great. This problem is we've solved it statistically. We just want to actually get a good algorithm. So how do we actually think about getting algorithms here? I like to think about this by some connection to like representation learning, which is like, people are doing it in supervised learning and all these places. So here's like a basic idea. So if I told you the latent state, then there's just a discrete number of them. There's not that many. And so you could just run like UCBVI or some other tabular RL algorithm there. And that would enable you to explore the whole environment. Of course, we don't know the latent state, but maybe an idea is to try to learn how to learn the latent state and then run a tabular algorithm. So learning the latent state, we like to call it decoding, because you see an observation, you decode the latent state, and then you run a tabular algorithm. And decoding the latent state is a form of representation learning, because you take some complicated object and you find a way to represent it in some simpler way that preserves all the information that you care about for your problem. So that's representation learning. It also kind of makes the algorithm design a bit modular, because you can sort of like separate out the process of decoding the latent state from the process of exploring by using a tabular algorithm on your learned state representation. So this is the kind of algorithm that we've been thinking about. And this is some, silly picture about what's going on. You have this image, you pass it through a neural network and you get some guess for the position of the agent somehow. Okay, but when we're operating with images, somehow we don't want to do enumeration. And instead, we sort of want to assume that we can solve optimization problems over the function class efficiently. So I still sort of want my results to be quite abstract, and I want to operate on, I want to be able to accommodate many different function classes when I design an algorithm. But if I don't tell you anything about the function class I'm using, somehow it could be completely unstructured, and then I have no hope except to do enumeration. So instead, what I'm going to assume is like, you give me a function class, and I'm going to assume that I can actually solve like supervised learning problems over the function class. And this is sort of like a reduction framework. It's again, kind of to make the algorithm design modular, right? Someone in our community has, really studied, and we really understand, I guess to some extent, how to solve, supervised learning problems over various function classes. And I'm just going to like inherit those results via a reduction. So I can focus on like how to find the right prediction problems and how to do the exploration. So this is a kind of approach. And this sort of leads to, I think, kind of a fun game or puzzle where you like try to write down various prediction problems and reason about what structure of the MDP can you uncover by solving this prediction problem. And I think the one thing to emphasize here is that this is not actually like an unsupervised problem, because so, you have these images and they correspond to different latent states, and maybe you could do clustering and that's fine, but you actually can do something much more because you actually have the dynamics in the process, right? So you can look at the actions and these kinds of things, and you can try to make various prediction problems using all these quantities that you actually see. So we've spent a long time trying to do this and write down various things. This one is like an unsupervised approach where you just take the state, you like pass it through some, I don't know, quantizer, and then you try to recover the states, and you hope that this will, preserve the actual state information. Some other things you could try is like, maybe you have some guess for a decoder, and you can take a state and, apply your guess for the decoder and get a predicted latent state. And then you can use like the next state and try to predict what the previous state, you can use the next observation and try to predict what the previous state was. So this is some sort of backward prediction about the previous latent state. So you can do stuff like this. You can also do things like contrastive learning, where you collect sort of two sequences of state, action, next state, and you try to predict which ones are actually temporally related and which ones are not. So you're going to create like this fake transition where I visited X1, I took action A1, and then I saw X2 prime. That's like a fake transition. And this, you can just solve a binary classification problem where you try to differentiate between real transitions and fake transitions and stuff like this. So this is quite fun. You can like, basically the way we've been thinking about this is you like write down some problem and then you derive what the Bayes optimal predictor is, and you kind of stare at it and you see like, what can you discover about the MDP from this Bayes predictor? And then the statistical analysis will sort of, hopefully it's kind of robust in the sense that if you're near the Bayes predictor, you actually recover a similar MDP structure. So we've done this, and like, here's the kind of thing that you can sort of prove. This is a bit informal. So here, if the latent states are reachable in some sense, like for every state, some policy can hit it with probability eta, and various prediction problems that you create are realizable, then you can learn a distribution over a few policies. That's what the psi is, such that somehow your policy cover actually visits. Yeah.
I think we have to wrap up in 3 minutes.
Okay, I'm almost done. Okay. So such that you actually cover all the states that can be visited by a policy. So for any policy, the probability that that policy hits the state is less than the probability that your cover hits that state. And you can do it in polynomially many samples and via reduction to supervised learning. And so this one, we actually use contrastive learning, and then we use sort of like kind of tabular methods to do exploration. And Dipendra Misra has actually implemented this thing, and he ran it on some hard exploration problems, and it does kind of work. Let me skip the next one. You can also do representation learning in the low rank MDP. We have a result on this that I think is kind of cool, and you can check out the paper if you want to learn more. And there's now a growing body of work on this kind of thing, and we've linked to many of these papers in the tutorial references, or come talk to us if you want to learn more. And I think that's it. So let me just wrap up. So I guess the main takeaway, I think, is that RL is not really like supervised learning, and indeed you require strong assumptions. We do have some fairly comprehensive understanding of what is statistically possible, although there's still some work to be done here. And the algorithm design, I think, there's a lot of work to do. So right now we make quite strong assumptions, and the guarantees are not what is suggested by the information theory. And more generally, there's just like a huge theory practice gap in reinforcement learning. And so there's lots and lots of work to do. There's many subtopics that we didn't cover, and many unresolved issues. So if you want to work on this topic, I would strongly encourage you to do so. It's been quite fun, and there's many things that we don't understand. So yeah, thanks for tuning in. And again, if there's any questions, you can ask now, you can find us later, or send us email. Thanks. Any question? Yeah, maybe I'll explain the contrastive. Maybe can you find me like right after, and I'll explain it to you. The contrastive learning. Okay, and then wait, Surby wanted me to make an announcement. Oh yeah, so now there's a social time and games. So please go into the garden and hang out and have some fun. And I don't know, maybe take a break.
Yeah, let me add to that. After that, we have a session to remember Matthew Brennan, which is going to be a part talking about his life and a part talking about his amazing work. He got the Gold Best Paper Award last year, which that will be discussed by Guy Bressler. And then after that, we have a WIMLT panel and social. So please stick around and see you at the garden. And thanks, Akshay and Wen, for this amazing tutorial.
And thanks, Surby, for organizing. She's done like a ton of work to make the conference very seamless. And okay, let's go to the garden for a hangout. Bye-bye.